Hi. So I always wanted to make something long form, hour long plus videos. And I'm kind of inspired from like videos like Dr. Angela Collier or Professor Dave Explains, stuff like that. And I really like find value in such things because honestly, how much information can you get from like a 5-minute video? Not much. But when videos are like long, it lets information kind of breathe and you kind of have time to let sinking stuff, and you could put it as background noise for when you have work to do or something. That's what I usually do. And I think this long form video stuff is like very important because like I said, it lets ideas breathe, but also it's like a combat against ever shortening attention span for people. So today I want to talk about quantum mechanics. And yeah, I will start kind of to talk about a little bit of history of quantum mechanics, a little bit of the physics, and then like maybe talk about the measurement problem and some quantum mechanics interpretations. Although I don't really find those all that interesting as many people think, as many people like tend to do, but I'm going to talk about them nonetheless. And then I'm going to talk about some cool experiments and how we actually managed to formulate this amazing part of physics. And yeah, I will probably end this on like what we currently know and what we currently don't, and do some like a closing statement like I usually do. Like, you know, like the best part of physics is that we don't know much about it. Something like that. I know I just burned the ending for you, but I'll probably try to make it a little bit more interesting than that. So without like further ado, I'm going to start talking about the history of quantum mechanics. So before the 20th century, physicists believed that the universe is mostly figured out. Reality was seen as a giant clockwork of mechanism, smooth, continuous, perfectly predictable, it's deterministic. If you knew the exact initial conditions of the system and the positions and the velocities of all particles, then in principle you could calculate everything that would ever happen to the system. And like this was, the Newtonian spirit. Newtonian mechanics and Maxwell's electromagnetism, they just showed that, like, not showed, it hinted at the universe, that the universe ran on, laws that have no room left for randomness, for ambiguity. It's just all deterministic, it's all predictable, right? And Pierre Simon Laplace even imagined that an all-knowing intelligence, he later called it, like it's later coined as Laplace's demon, and this, all-knowing intelligence could compute the entire past and the future of the cosmos just from its current state. So in short, the word was, like I said just now, deterministic, it's continuous, it's intuitive, and it's always understandable. You could always, reduce information to bases that everyone could understand. Newton's laws of gravitation, they're simple. They teach them in high schools. So, yeah, every huge concept in the universe could be boiled down to a simpler law that is understandable. But then the cracks began to show. So the first crack came not from something huge and like we couldn't understand this before. No, no, no. It came from something so ordinary and so simple as heat and light. And when physicists try to calculate the spectrum of light that is emitted by a perfect absorber, it's called a black body, they failed spectacularly. The equations predicted that a black body should emit infinite energy at high frequencies near the ultraviolet spectrum. And this led to what is now known as the ultraviolet catastrophe. There are millions of videos on this, and they're really well explained, better than I could show you in this bit. But the gist of the story is that in 1900s, in 1900, I don't know how to say that, Max Planck fixed this program. Oh my god, this program. Max Planck fixed this problem by introducing a radical idea. And that is quantum. Yes, I said the word. I said it. energy isn't continuous. It comes in packets of discrete energy, in discrete, like I said, in discrete packets of energy, and they call them quanta. He didn't fully grasp the implications of his postulation. It was more like a mathematical, tool to facilitate his equations and his predictions, rather than anything like well thought. But this was the rather sloppy birth of quantum mechanics. So a few years later, in 1905, Albert Einstein was writing his paper on the photoelectric effect. And the photoelectric effect is another phenomenon that classical mechanics just can't explain. When light is shown on a metal surface, it can eject electrons from the material. But experiments show different things from what the theory should show. Let me explain. So, according to classical wave theory, increasing the light intensity should increase the energy it's emitted, that is emitted by the electrons. And there should be a delay before the electrons are released, and the time that we not show, shine. Oh God, that we shine the light beams, right? But yeah, in reality, electrons were ejected instantly. That's the first observation. And the second one is that the energy of the electrons, it didn't depend on the intensity of the light beam per se, but it depended on the light's frequency. So even if we shone like extremely bright light at very low frequencies, it failed to eject any electrons at all. And in 1905, like I was saying, Albert Einstein proposed the explanation that light itself is made of discrete packets of energy. And not he, but like the general consensus is that these are called photons. And rather than being just continuous waves, photons were also packets of discrete energy. And that's my WhatsApp going on. Yeah, each photon carries the energy that is predicted by Planck's equation. E is equal to hv, h being Planck's constant, it's a fundamental constant in the universe, and v being the radiation frequency. So only photons above a certain threshold of frequency have enough energy to knock electrons out of the metal. The intensity of light simply tells us how many photons are arrive and not how energetic each one is. And it was this discovery and this idea that landed him the Nobel Prize. And then came the mystery of atomic spectra. Very basically, the concept is that when elements are heated or excited via photon beams or electron beams, they emit light at a very specific sharp wavelength rather than a continuous rainbow. And classical models of the atom with you can imagine like a bunch of electrons kind of orbiting the center of the nucleus. The center of the center of the nucleus. So like planets around the sun, but these specific models, they couldn't explain the specific phenomenon of how light is emitted at specific wavelength and not just a continuous spectra. So in 1913, Niels Bohr proposed that electrons don't move in just any orbit and that they're restricted to specific quantized energies of level. I mean, they are restricted to specific quantized energy levels. Oh my god, I spoke that so badly. And that means that they can jump between them, emitting or absorbing energy in like discrete amounts. Again, we are shown that energy isn't, continuous. It's rather quantized. Energy is quantized. Yeah. Awesome. This fact that energy is quantized and that light was rather a packet of energy and not just a wave, it kind of shook our reality at its core. And in 1924, I think Louis de Broglie, I don't know how to pronounce his name, I'm so sorry. Louis de Broglie extended the idea of wave particle duality to literally everything, not just photons. So he suggested that electrons, atoms, maybe all matter have wave-like properties and particle-like properties. And experiments, they showed that. It showed that electrons could diffract and interfere just like light. Here you can think of the double slit experiment and how it kind of drove the point home. So when particles like electrons, single tiny individual particles, are sent through narrow slits, they don't behave in the classical manner. You wouldn't see points where the slits are and no points where the slits aren't, where the wall kind of stops the electrons from moving. No, instead you'd see that they build up an interference pattern, characteristic of waves. Even when fired one at a time, each electron seems to interfere with itself, as if like taking multiple paths at once. Veritasium has an amazing video on this. Maybe I'll link it in the description. I don't think I have the power to link stuff in my description yet because I haven't verified my account. But yeah. Anyways, the moment you try to observe electrons, and I know like the word observation gets thrown a lot in this context. I mean clearly when you try to shine photons at it so that we can see it, therefore collapsing its superposition state. But yeah, that's the point that I'm trying to make. The moment you observe them by shining photons at it, shining electrons at it, shining any particle at it, to try to see which slit it went through, the pattern disappears and the electron starts to behave like a particle again. This, again, is like direct consequence of the photon collapsing the superposition state of the electron, as the photon being the thing that we're throwing at the electron so that we can observe it. And yeah, that collapses the superposition state. So it's not nothing mystical. Please don't. No, you're not a crazy thing that collapses the universe when you see it. Please, that has not. That's meaningless nonsense. Please. Anyways, I hate quantum mysticism. It's really bad because quantum mechanics is so beautiful and it doesn't need all this mysticism for it to be beautiful, and yet people only seem to be interested in it just to drive home this like idea that we're some kind of gods ourselves or something. No, oh, no. You're not the person that is collapsing the electron state. It's the photon. It's the photons that are needed for your eyes to function, or else you won't see the electron. That's why. Oh god. Anyways, rant over. These, like I was trying to say, these at start they started as mathematical concepts to fix the ultraviolet catastrophe, and as like experiments were done, and the photoelectric effect, the atomic spectrum being worked on, and the double slit experiments and so on and so forth, they have shown that they're not just mathematical concepts. In fact, they're real. Quantum mechanics are real. And by the 1920s, it was clear the universe doesn't follow the rules of classical mechanics. It's not predictable. It's not deterministic. It's probabilistic. It's chaotic. It's very interesting. It's much more interesting than we thought it was. Even though back then we still thought that the universe is still interesting, but now it's much more interesting than we thought, and it doesn't follow the rules that we thought it did. And something deeper and stranger and far less deterministic is at play, and that's quantum mechanics for you. Okay, so now we know a bit of history about how quantum mechanics emerged. But what is quantum mechanics? I mentioned something earlier about collapse of superposition and interference and observation and stuff like that. But what does that mean in terms of physics? Let's start from ground zero. At the very, very heart of quantum theory is this object called wave function. It's usually written as the Greek letter psi, and this is not a physical wave in space like sound or a sound wave or a water ripple. It's a mathematical object. It's a function that tells you everything that can possibly be known about a system. If you hand me a psi or her psi, I don't know, do I pronounce the P? It's like psychology. Do I pronounce the P? No. So I'm going to call it psi. If you hand me a psi, in principle, I would know everything. Where a particle should be, could be, how fast it could be moving, and how it might behave in the future. It's complete description. But there's the catch. Psi doesn't tell you what it is. It tells you what it could be. To get an actual prediction from it, you need the Born rule. The rule says that if you take the absolute value of psi and square it, it should give you a probability density. Or, in other words, psi doesn't give you a definite outcome, it gives you the probability of the outcome. The theory doesn't tell you where the electron is, it tells you the likelihood of the electron being in a specific part of this universe. So, a good analogy of the electron problem, not, if we know its position, we wouldn't know its velocity type of question, is that I saw this on Reddit this morning, and it says, like, imagine the electron is like an ocean. It could, like, not an ocean, it's a wave in the ocean. The wave could be anywhere in the ocean, but the psi function tells us the likelihood of the wave existing somewhere specific in this ocean. And if we square that, we get the probability that it's there in that specific space. And yeah, if we know where the wave could possibly be, then we lose a bit of information about its velocity. This is called Heisenberg's uncertainty principle. Maybe I'll come back to this in a bit. But now I'm interested more about how psi changes over time. So there's this thing called the Schrodinger's equation. It's a differential equation that acts like on the wave function and tells you how it evolves over time and space. There's the interesting part. The Schrodinger's equation is completely deterministic. This means that if you know psi at one moment, you can calculate exactly where it will be later. This mainly means that there is no randomness and no hand waving. It's, yeah, it's very deterministic. And between measurements, classical mechanics is as clean and as exact as classical mechanics, if not a bit more tedious with the calculations. But there is a subtle problem with the Schrodinger's equation, and that it's built on non-relativistic assumptions. It was originally formulated for particles moving much slower than the speed of light and in a flat, not Newtonian time. It assumes there's a single universal time variable that is sticking the same everywhere, which is something Einstein's relativity completely rejects. So, relativity says that time and space are woven together, and that time flows differently depending on where you are and how you're moving. The Schrodinger's equation ignores that. It treats time like an external absolute parameter, it treats time like an absolute variable. It's a parameter. You know how there are games where you have a timer up there? Yeah, imagine that timer everywhere in the universe. There's just no built in respect for relativity, and there's no speed of light limit. In fact, in its original form, information in the wave function could propagate faster than light itself, which is a no go for, you know, relativity and our consensus with that. Because, relativity is a very, very successful theory of physics. And we can't have two successful theories of physics arguing with each other so casually. So physicists, like they are always doing, tried to fix this. And they came up with things like the Klein-Gordon equation and the Dirac equations, which do respect relativity, but those come with their own set of complications. The particles can be created and destroyed, and the negative energies appear, and suddenly quantum mechanics has to merge with field theory, and there's that bit where we have quantum field theory, which kind of replaces particles with fields and quantizes those fields instead of trying to push Schrodinger's equation to its limit. But here's the thing, I know Schrodinger's equation has its set of problems, but we still use it. Why, you may ask? That's very wise. So we use it mainly for chemistry, like atoms, molecules, semiconductors, yeah, all of that stuff. Although it's not the ultimate final version of quantum theory, but it's used because it works. Like in experimentation, for example, it predicts what the experiment is going to say with ridiculous accuracy, better than any other like theory. Speaking of collapse, let's talk about another troublesome area of quantum mechanics: measurement. So the theory says that if you perform a measurement, so let's say we're measuring the position of a particle, psi shouldn't keep evolving smoothly. Instead, it suddenly collapses or projects into one specific outcome. It's called an eigenstate of whatever you're measuring. If psi, the wave function, said that our electron could be in 5 different states with different possibilities, the act of measuring it forces the electron to pick one state. And this collapse is, like I said, not measured and not described by Schrodinger's equation, so it's an extra rule. And now we have two kinds of evolution: deterministic and probabilistic. For deterministic evolution, when the system is unobserved, it's going according to Schrodinger. And for the probabilistic evolution, when collapse happens and the system is measured, then we follow the measurement postulate. And to make sense of all of this mumbo jumbo, mechanics uses a more abstract mathematical framework. It's called Hilbert space. Hilbert space is sort of where wave functions live. It's it's a space where we can make superpositions, and those are like combinations of possible states that psi could take, or actual physical quantities like energy and momentum and velocity and so on. And we can represent those possibility states by operators that act on psi. Hilbert space is mathematically sound, but conceptually it's a bit questionable. So we have this contrast between rule 1, the Schrodinger's equation, it's deterministic, and I just explained that. And there's rule 2, the measurement postulate, and it's probabilistic. And what's here? That's a problem. Yay! So, why is it that when we measure something, goes from being deterministic to being probabilistic? Right? Why is measurement so special? And again, measurement isn't like about us humans staring at an electron. Most times you don't see an electron. It's measurement is a physical interaction. It's something that forces a system to take a definitive value of an observable. It's a detector taking a photon scattering off an object, so us, mere humans, can observe it. That is observation, not just us being there and going like, oh, I see the universe, therefore I collapse its state. No, that's not how it works. So let's go back to the issue at hand. Schrodinger's equation by itself says that all systems, detectors, particles, cats, and us humans, even measuring devices, should evolve smoothly and stay in a superposition. And there's no moment in the equation where it says, okay, now collapse, because something interacted with it. The puzzling thing is, when does collapse happen? Does it happen at all? Is it physical, or is just a mathematical trick to make the math work? Why do we see single outcomes rather than superpositions, even though the math never forces one to occur? And this is why Schrodinger used the cat analogy. It's sort of a joke. It's not a real thing. Please stop using it as like an analogy thing. It's not. I'm so tired of seeing Schrodinger's cat being used to explain quantum mechanics. It's not. It's a joke. Schrodinger made it to joke about how absurd applying quantum mechanics to real life is. It's a joke. Again, he was just saying that if your theory suggests that cats could be half dead, half alive, maybe the theory is problematic. Maybe it has a problem. If us upscaling the theory from going to relatively slow microscopic particles into macroscopic objects, and the analogy doesn't work if the interpretation leads to a superposition of macroscopic objects and we don't observe that superposition of macroscopic objects, then something is fundamentally wrong or our vision is just incomplete. And the same could be said with Wagner's friend. It's not like, ooh, consciousness. It's also showing what happens if we take quantum mechanics to its extent. One person's collapsed state is another person's superposition, and the theory doesn't tell you who's right. So the takeaway isn't like, oh, consciousness or like the cat is both dead and alive. The takeaway actually is that where the hell does this line between maybe and definitely actually happen? And why does it happen? And that is the measurement problem in one sentence. Okay, I know that in the introduction of this video I said that I'm going to talk about the interpretations of quantum mechanics, but honestly, I really don't want to. Because this is a subject that is always quoted in the layer of quantum mysticism that I find very rotten and dishonest and just disingenuous, It's never portrayed correctly what quantum mechanics really is whenever there's talk about these interpretations. And I find that really disheartening because quantum mechanics does not need these fancy, weird, unconventional interpretations for it to be actually cool. Like I just showed you, there's lots of cool things that don't have to tip into, oh, what if there's a billion gazillion words that we cannot prove exist or something. It's stuff like that. I'm not really into that stuff. So I'm going to talk about experiments. So the first thing that I want to talk about in this section is Bell's theorem. So in 1964, John Bell asked a simple question, and that is like we just asked it a little bit ago. But what if quantum mechanics is just incomplete? Which is valid, like valid question. And maybe there are hidden variables underneath, like little classical instructions that particles carry with them, making the outcome kind of deterministic. And maybe all the probabilities are just us not knowing those instructions. But Bell proved something quite shocking. No theory based on local hidden variables can reproduce the predictions of quantum mechanics. He wrote down inequalities, mathematical limits that any local realist theory must obey. These are now called the Bell inequalities, and a simple analogy we can try to use to visualize this is imagine two people opening identical mystery boxes in different rooms. If the boxes were pre programmed with matching answers, the correlation between them could only go so far. But the correlation quantum mechanics predicts and that we measure kind of go beyond what any classical pre programming allows. Allen's aspects experiments in the 1980s kind of tested this directly. So we have two entangled photons that are created and sent to distant detectors. Each detector randomly chooses a measurement setting, and the correlations of the outcomes are measured. The result is that Bell's inequalities are violated, meaning the local hidden variables cannot explain the result, and that quantum mechanics predictions, even the probabilistic ones, yes, they are correct. Entanglement is real. The measurement outcomes of one particle affect the correlations with the other, instantaneously in a sense, though without transmitting usable information faster than light itself. Again, I remind that Bell's inequalities are these, set of limits that non quantum mechanics theories must obey. And yeah, they were violated. This very simply means that no local realist theory can reproduce quantum predictions, and that the universe cannot be both local or no faster than light influence and deterministic in the classical sense. Something has to give. Either we accept non locality, that entanglement is real, or reject realism, and that means that properties don't exist until measured. Since we're talking about measurement, there's this gag. Lots of Einstein's so called quotes are not his actually, but let's assume that if Einstein said this, he would have said something along the lines, oh, it's entanglement is spooky action at a distance or something. And yeah, that line is used to mock entanglement. And it's, although I don't really quite trust that, because lots of things have been said in his mouth, like put in his mouth, he wouldn't say this. I don't believe that the person who did the photoelectric effect would probably say something like this, but let's assume he did. And let's assume that he thought it showed quantum mechanics had to be incomplete. But if we assume this, then we have to disregard a huge body of experimentation that we have currently. Because experiments say totally otherwise. Entanglement isn't just like an undeniable part of reality, it's literally so fundamental that it's a fundamental feature in our universe. And when two particles are entangled, measuring one instantly tells you something about the other, even if it's light years away. I know this process doesn't transmit information faster than light, but what it does absolutely is that it violates classical expectations about separability. Okay, I realize how absurd this might sound to someone who doesn't know these things, but let me explain the first part on why it doesn't transmit information faster than light. So, even though the correlation appears instantaneously, you cannot use this to kind of send information. You can't control the outcome of the measurement because it's random. The other particle's measurement is also random, but the randomness is correlated. Only when you later compare the results at normal, sub light speed intervals, do you see the correlation. So relativity isn't violated here. And on the second part, on why it kind of violates classical expectations about separability, classically speaking, we assume that objects have their own independent properties. And if two particles are far apart, when what you do to one shouldn't affect the other. Entanglement kind of breaks this. Two particles can no longer be independent. They're not separate. Their states are inseparably linked, and no matter the distance, they are entangled and they're linked. And that's the spooky action at a distance that is usually put in the mouth of Einstein. Like I said, it's really hard to believe that the father or one of the fathers of quantum mechanics would say this about his son, basically. Uh, but maybe I'm wrong. Maybe he did. I don't know. I haven't lived in the early 1900s. Okay, now that is out of the way. I want to talk about a bit about, quantum gravity, string theory, loop quantum gravity, stuff like that. I'm not really well versed in this stuff, but I wanted to communicate a bit about it and how it's important and it's interesting. So, this is a section of what do we know and what do we not know. And one of the biggest stuff that we're like the physics community is working on currently is quantum gravity. It's like an attempt to merge quantum mechanics with general relativity. And right now, these are the two pillars of physics. They are good at what they do, but together they're not very compatible. Quantum mechanics works with very small particles. They're very slow. Its precision is absolutely amazing. But when we're dealing with bigger object and faster object, then quantum mechanics doesn't happen. It doesn't work as magnificently. And that's where general relativity rules at the very large and fast things. But when we're trying to describe things that are sort of in between, like black holes or the Big Bang, both of these theories, they're kind of essential. We can just say, yeah, we're gonna work with relativity when we need relativity, and we're gonna work with quantum mechanics when we need it. No, sometimes we need both to describe our universe in its entirety, and just not have these sort of blind spots. And yeah, this is where quantum gravity comes into play. Instead of having two separate languages to describe our universe, we get to create one singular universal language that could describe the entirety of our universe, although it has its ins and outs in terms of problems. But it's a noble attempt that is very much appreciated. And another proposed solution that physicists have proposed is string theory, which should suggest that everything, particles, forces, and even space itself is made of tiny vibrating strings. This has lots of mathematical rigor, but no seemingly clear way to experiment and empirical work, you know? It's a literally super interesting, mathematical framework. And I'm not really well versed in this, and I don't have a say in this. I don't even have a say in any of this. Yeah. But I really like to talk about it, and you could fact check me and tell me if I'm doing anything wrong here. So I really appreciate that actually. And all I know is that in string theory, our universe is kind of made up of strings, vibrating strings that make up different particles. Each particle is different vibration mode, and same with gravity actually. It all sort of emerges from vibrational modes. And there's much more. All of these are attempts to reconcile the deep torsion that is plaguing, quantum mechanics and relativity. And it's all attempting to create a theory that works on all scales. But so far, we don't really have a final answer. Or else this video would be titled something else entirely, and like the world would be so boring. Or is it? I really don't know. We don't live in that world, so I don't have a prediction for how it. I mean, I could make a sensible prediction and that it would be super boring. There's still some stuff to work on, but still, it'll be boring if we have an M theory right now. I guess what I mean to say is that our universe would be less interesting than it is right now if we had the M theory, and that's why working on it is better than actually achieving it, I think. And I think that's all I wanted to say. I've been wanting to make this video for so long, you have no idea. And we just reached the end of it. So I want to take this moment to kind of reflect back at it a little bit. I guess the video's purpose is to show you how quantum mechanics works perfectly. It's flawless and it predicts everything that the experimentation shows, and it's incredibly accurate at what it does. And yet, despite all of this incredible flawless prediction and like accuracy, we still don't know what any of it means. I mean, we do kind of like the wave function, it evolves deterministically, and then suddenly it collapses and it becomes probabilistic in nature, and particles behave like waves and particles at the same time. Tangled pairs exist and they kind of break our classical intuition. And I think what I really wanted to do most with this video is just show the world that quantum mechanics isn't weird. What is weird is a world without quantum mechanics. Because it describes the only kind of world that is real, that is possible. I mean, it's not perfect, like I showed you. There are lots of ins and outs. I don't know if I'm using the word ins and outs perfectly, but you get it, right? There are problems with it. But that's okay. It describes what it describes best perfectly. And yeah, there are like attempts at finding solutions and reconciling the, like I said, the tension, the torsion between relativistic mechanics and relativistic physics and quantum mechanics. I merged those words so badly. And yeah, I really hope that my point comes across well enough and that I'm not rambling for most of the video. Because I've been recording for 3 hours straight. Oh my god, I think that's it. Goodbye.